Welcome, dear viewers, to my channel, Cozy Gamer, where we explore the most mind-bending concepts in science and philosophy. I'm your host, Dev, and today we're diving deep into a topic that has puzzled humanity for millennia: the nature of time. Is time linear, moving forward like an arrow? Is it cyclical, repeating in endless loops? Or is it something else entirely? Buckle up, because we're about to embark on a journey through the very fabric of reality itself. 1. The everyday experience of time. Let's start with something we all know intimately: our everyday experience of time. From the moment we wake up to when we lay our heads down to sleep, time seems to flow in one direction. We remember the past, live in the present, and anticipate the future. This intuitive understanding of time as a linear progression is deeply ingrained in our psyche and culture. Think about how we structure our lives. We have schedules, deadlines, and plans for the future. We celebrate birthdays, marking another year past. We study history to learn from past events and make predictions about what's to come. This linear conception of time is so fundamental to our existence that it's hard to imagine any other way of experiencing it. But is this everyday experience of time the whole story? As we'll discover, the nature of time is far more complex and mysterious than our intuitions might suggest. 2. Historical perspectives on time. To truly understand our modern conceptions of time, we need to take a step back and look at how different cultures and civilizations have understood time throughout history. In many ancient cultures, time was seen as cyclical rather than linear. The ancient Greeks, for example, had a concept of eternal return, the idea that the universe and all existence has been recurring and will continue to recur in a self-similar form an infinite number of times across infinite time or space. This cyclical view of time was also prevalent in many Eastern philosophies. In Hinduism and Buddhism, the concept of samsara represents the continuous cycle of birth, life, death, and rebirth. Time is seen not as a straight line, but as a wheel that turns endlessly. Ancient Mayan civilization had a particularly complex view of time, involving multiple cycles of different lengths interwoven with each other. They saw time as both cyclical and linear, with grand cycles spanning thousands of years. In contrast, the Judeo-Christian tradition introduced a more linear concept of time to Western thought. The idea of creation, fall, redemption, and final judgment presents history as a sequence of unique events moving towards a final goal, rather than an endless cycle of repetition. These diverse historical perspectives remind us that our current understanding of time is shaped by cultural and philosophical influences, not just scientific observation. 3. The arrow of time. Now, let's turn to how modern science views time. One of the most fundamental concepts in our scientific understanding of time is the arrow of time, the idea that time flows in one direction, from past to future. This concept is closely tied to the second law of thermodynamics, which states that the entropy or disorder of an isolated system always increases over time. This law gives time a direction. We can distinguish between past and future because entropy increases as we move from past to future. Consider a simple example. If you drop an egg and it shatters on the floor, you can easily tell which event happened first, the intact egg or the broken mess. You'll never see a broken egg spontaneously reassemble itself, because that would violate the second law of thermodynamics. This arrow of time is evident in many aspects of our universe. 1. Cosmological arrow. The universe is expanding, moving from a state of lower entropy, the Big Bang, to higher entropy. 2. Thermodynamic arrow. Heat flows from hot objects to cold ones, never the reverse. 3. Psychological arrow. We remember the past but not the future. 4. Causal arrow. Causes precede effects. These arrows all point in the same direction, giving us a consistent sense of time's flow. But as we'll see, this seemingly straightforward concept becomes much more complicated when we look at the fundamental laws of physics. For time in classical physics. To understand how our modern view of time developed, we need to look at how it was treated in classical physics, particularly in the work of Sir Isaac Newton. In Newtonian physics, time was seen as absolute and universal. Newton described time as flowing equably, without relation to anything external. In other words, time was thought to pass at the same rate for everyone and everything in the universe, providing a fixed background against which all events occur. This view of time aligns well with our intuitive understanding. It suggests that if we could somehow step outside the universe and observe it, we'd see all events unfolding in a universal cosmic time. However, this neat and tidy view of time was to be dramatically upset by developments in physics in the early 20th century. 5. Einstein and relativity. The publication of Albert Einstein's theories of special and general relativity in the early 1900s revolutionized our understanding of time. Special relativity, published in 1905, showed that time is not absolute but relative. The theory demonstrates that the passage of time depends on your frame of reference. If you're moving very fast relative to someone else, time will pass more slowly for you than for them. This effect, known as time dilation, has been confirmed by numerous experiments and is even accounted for in the GPS systems we use every day. General relativity, published in 1915, went even further. It showed that time is intimately connected with space, forming a four-dimensional continuum called spacetime. In this theory, gravity is not a force but a curvature of spacetime caused by mass and energy. One of the most mind-bending implications of general relativity is that massive objects like black holes can actually warp time. If you were to approach a black hole, time would pass more slowly for you than for someone far away from it. These theories completely upended the Newtonian view of time as absolute and universal. They showed that time is flexible, can be stretched or compressed, and is deeply intertwined with space and matter. 6. Quantum mechanics and time. If relativity challenged our understanding of time, quantum mechanics threw it into complete disarray. At the quantum level, many of our intuitions about cause and effect break down. Quantum entanglement, for example, seems to allow for instantaneous communication between particles, regardless of the distance between them. This spooky action at a distance, as Einstein called it, seems to violate the principle that nothing can travel faster than light. Even more strangely, some interpretations of quantum mechanics suggest that the future can influence the past. The delayed choice quantum eraser experiment, for instance, seems to show that a decision made about how to measure a particle can retroactively determine its past state. These quantum phenomena have led some physicists to question whether time is fundamental at all, or if it emerges from more basic quantum processes. 7. Block universe theory. One intriguing idea that arises from relativity is the concept of the block universe. This theory suggests that past, present, and future all exist simultaneously. In this view, our universe can be thought of as a four-dimensional block, where time is just another dimension like length, width, and height. All moments in time past, present, and future exist together in this block. The block universe theory doesn't deny that we experience time as flowing from past to future. However, it suggests that this flow is an illusion, a result of how our consciousness moves through the time dimension. This idea has some fascinating implications. If all of time already exists, does that mean the future is predetermined? What does this mean for concepts like free will? While the block universe theory is consistent with relativity, it's important to note that it's not the only possible interpretation, and it still doesn't explain why we experience time in the way we do. 8. Cyclic models of the universe. Now, let's return to the idea of cyclical time, but from a modern cosmological perspective. Some theories of the universe propose that the Big Bang wasn't a one-time event, but part of an endless cycle of expansion and contraction. These cyclic or oscillating universe models suggest that our universe expands from a Big Bang, eventually slows and contracts back to a big crunch, then expands again in a new Big Bang. One version of this idea is the conformal cyclic cosmology, proposed by mathematician and physicist Roger Penrose. This theory suggests that the universe goes through repeated cycles of expansion, but each cycle is preceded by the complete gravitational collapse of a previous universe. Another cyclic model is the ekpyrotic universe scenario, developed by Paul Steinhardt and Neil Turok. This model proposes that our universe is one of two three-dimensional worlds in a higher dimensional space. These branes, short for membranes, collide periodically, each collision causing a Big Bang-like event. These cyclic models are intriguing because they potentially solve some problems with the standard Big Bang theory, such as the flatness problem and the horizon problem. However, they also face significant challenges and are far from being widely accepted in the scientific community. If any of these cyclic models turn out to be correct, it would suggest that time on the grandest scale is indeed cyclical. However, within each cycle, we might still experience time as linear. 9. The problem of time in quantum gravity. As we delve deeper into theoretical physics, we encounter what's known as the problem of time in quantum gravity. Quantum gravity is the holy grail of modern physics, a theory that would unite quantum mechanics and general relativity. However, attempts to create such a theory have run into a fundamental issue with how time is treated. In quantum mechanics, time is treated as an external parameter, not as a dynamic variable. But in general relativity, time is part of the dynamical system itself. When trying to combine these theories, we run into trouble. Some approaches to quantum gravity, like loop quantum gravity, suggest that at the most fundamental level, time might not exist at all. Instead, our experience of time might emerge from more basic quantum processes. This idea is encapsulated in the Wheeler-DeWitt equation, a key formula in quantum gravity. Strikingly, this equation doesn't include time at all, leading to what's called the frozen formalism, a picture of the universe where nothing ever happens. Of course, we know that things do happen, and we experience time passing. Reconciling this experience with the timelessness suggested by some quantum gravity theories is one of the biggest challenges in theoretical physics today. 10. Emergent time. Given the difficulties in reconciling time at the quantum level with our everyday experience, some physicists have proposed that time might be an emergent phenomenon. In this view, time is not a fundamental feature of reality but emerges from more basic quantum processes. This is similar to how temperature emerges from the collective behavior of particles, even though individual particles don't have a temperature. One intriguing approach to emergent time comes from the study of quantum entanglement. Some researchers have suggested that the way quantum systems become entangled over time might give rise to our perception of time's arrow. Another perspective comes from causal set theory, which proposes that space-time is fundamentally discrete, composed of elementary events with causal relationships between them. In this view, what we perceive as the flow of time emerges from the increasing number of causal connections as the universe evolves. These ideas are still highly speculative, but they offer potential ways to resolve the conflict between quantum mechanics and general relativity, and to explain how our everyday experience of time arises from a more fundamental timeless reality. 11. Time and consciousness. No discussion of time would be complete without considering the role of consciousness. After all, our subjective experience of time passing is a key part of what makes time such a puzzling concept. Neuroscience and psychology have revealed that our perception of time is far from perfect. Time seems to slow down in dangerous situations, speed up when we're having fun, and drag on when we're bored. These subjective experiences don't change the actual passage of time, but they do affect how we perceive it. Some philosophers and scientists have gone even further, suggesting that consciousness itself might be key to understanding time. The philosopher Henri Bergson, for instance, distinguished between clock time, the objective, measurable time of physics, and lived time, the subjective experience of duration that we feel in our consciousness. More recently, some researchers have proposed that our consciousness creates our experience of time passing by stitching together discrete moments into a continuous flow. This idea aligns with some interpretations of quantum mechanics, which suggest that reality might be fundamentally discrete rather than continuous. These perspectives raise profound questions. Is our experience of time fundamentally different from time as it exists in physics? Could time as we know it be a construct of our consciousness rather than a fundamental aspect of reality? 12. Time travel. No exploration of time would be complete without touching on the tantalizing possibility of time travel. While time travel remains firmly in the realm of science fiction, the laws of physics don't explicitly forbid it, at least not in all cases. Einstein's theory of general relativity allows for the possibility of closed time-like curves, paths through space-time that return to their starting point in both space and time. If you could travel along such a path, you would arrive back where you started before you left. One way this might theoretically be possible is through wormholes, hypothetical tunnels through space-time that could connect distant points in space and time. If we could create and stabilize a wormhole a feat far beyond our current technology, it might be possible to use it as a time machine. However, time travel raises numerous paradoxes. The most famous is the grandfather paradox. What if you traveled back in time and prevented your grandparents from meeting? Would you cease to exist? If so, how could you have traveled back in time in the first place? Physicists and philosophers have proposed various resolutions to these paradoxes, from the idea of parallel universes to the Novikov self-consistency principle, which suggests that any actions taken by a time traveler would already be part of history. While practical time travel remains firmly out of reach, these thought experiments push our understanding of time to its limits and highlight the deep connections between time, causality, and the nature of reality itself. 13. The thermodynamic basis of time. We've touched on the second law of thermodynamics earlier, but it's worth exploring in more depth because of its fundamental importance to our understanding of time. The second law states that the entropy, disorder, of an isolated system always increases over time. This law gives time a clear direction. We can distinguish between past and future because entropy increases as we move from past to future. But why does entropy increase? The answer lies in probability. There are simply many more ways for a system to be disordered than ordered. If you start with an ordered system and let it evolve randomly, it's overwhelmingly likely to end up in a more disordered state. This probabilistic nature of entropy increase has led some physicists to suggest that the arrow of time is essentially a statistical phenomenon. In principle, it's possible for entropy to decrease locally, but it's extremely improbable over large scales or long time periods. This perspective ties the arrow of time to the initial conditions of our universe. The fact that we experience time as flowing from past to future might ultimately be due to the fact that our universe started in a very low entropy state, the Big Bang, and has been becoming more disordered ever since. 14. Cultural and philosophical perspectives on time. While we've focused largely on scientific perspectives, it's important to recognize that our understanding of time is also shaped by cultural and philosophical ideas. Different cultures around the world have diverse concepts of time. Some, like many indigenous Australian cultures, have a more cyclical view of time tied to natural cycles and ancestral stories. Others, like many Western cultures, tend to view time more linearly, as a progression from past to future. These cultural differences in time perception can have profound effects on how societies function. For example, some cultures place great emphasis on punctuality and scheduling, while others have a more flexible attitude towards time. Philosophers have grappled with the nature of time for millennia. St. Augustine famously pondered, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." Some philosophers, like MacTaggart, have argued that time is unreal, merely an illusion of our consciousness. Others, like Bergson, have emphasized the importance of our lived experience of time as distinct from the time of physics. These cultural and philosophical perspectives remind us that time is not just a physical phenomenon, but a deeply human concept that shapes how we understand ourselves and our place in the universe. 15. The future of time. As we wrap up our exploration, let's consider what the future might hold for our understanding of time. Advances in physics could dramatically reshape our conception of time. If a viable theory of quantum gravity is developed, it could resolve many of the paradoxes and inconsistencies in our current understanding of time at the smallest scales. New astronomical observations might provide evidence for or against various cosmological models, potentially shedding light on whether our universe is cyclic or linear on the grandest scales. Developments in neuroscience and psychology could give us deeper insights into how our brains process and perceive time, potentially clarifying the relationship between objective physical time and our subjective experience of it. Advances in technology might allow us to manipulate time in new ways. While time travel remains unlikely, we might develop better ways to slow down or speed up biological processes, effectively altering the pace of time for living organisms. Cryogenics and suspended animation, for instance, could one day allow us to pause time for individuals, opening up possibilities for long-term space travel or medical treatments. Artificial intelligence and quantum computing could also play a role in our future understanding of time. These technologies might allow us to simulate complex systems and explore different models of time and causality in ways that are currently beyond our reach. As we continue to push the boundaries of our knowledge, we may find that our most fundamental assumptions about time need to be revised. The nature of time remains one of the deepest mysteries in science and philosophy, and future discoveries may lead to paradigm shifts as dramatic as those brought about by relativity and quantum mechanics. 16. Time and information. An emerging perspective in physics connects the concept of time with information theory. This approach suggests that the flow of time might be fundamentally linked to the flow of information. In this view, the arrow of time, the apparent one-way direction of time, could be a result of information being created or processed. When we observe or measure something, we're creating new information. This irreversible creation of information might be what gives time its direction. This idea ties into quantum mechanics, where the act of measurement plays a crucial role. The collapse of the wave function, the process by which a quantum system goes from existing in multiple possible states to a single definite state when measured, could be seen as a creation of information, and thus a marker of the passage of time. Some physicists, like Carlo Rovelli, have taken this idea even further. Rovelli's thermal time hypothesis suggests that time itself might emerge from quantum entanglement between particles. In this view, time is not a fundamental property of the universe, but rather a manifestation of the way quantum information is organized. These information-based approaches to time are still speculative, but they offer intriguing new ways to think about the nature of time and its connection to other fundamental aspects of reality. 17. Time and symmetry. Another important concept in our understanding of time is symmetry. In physics, symmetries play a crucial role in our fundamental laws, and the breaking of symmetries often leads to profound insights. Most of the fundamental laws of physics are time-symmetric, meaning they work the same whether time is running forward or backward. This is true for Newton's laws of motion, Maxwell's equations of electromagnetism, and even the equations of general relativity. However, as we've discussed, we observe a clear arrow of time in our everyday experience. This apparent contradiction between time-symmetric laws and time-asymmetric experience is a deep puzzle in physics. One potential resolution comes from the study of particle physics. In the 1960s, physicists discovered that certain rare particle interactions violate something called CP symmetry, charge parity symmetry. This CP violation, combined with another principle called CPT symmetry, implies that these interactions must also violate time reversal symmetry. While these time asymmetric processes are very rare and subtle, they suggest that at the most fundamental level, there might indeed be a difference between past and future built into the laws of physics. Understanding how these microscopic time asymmetries relate to the macroscopic arrow of time we experience is an active area of research in physics. It's possible that these tiny asymmetries, amplified over cosmic scales, could be responsible for the apparent flow of time in our universe. 18. Time in cosmology. Let's zoom out to the largest scales and consider how time fits into our understanding of the cosmos as a whole. In the standard Big Bang model of cosmology, time has a beginning, the moment of the Big Bang itself. Before this, our current theories break down, and we can't meaningfully talk about time as we understand it. However, this doesn't necessarily mean that nothing existed before the Big Bang. Some theories, like eternal inflation, suggest that our universe might be just one bubble in a vast multiverse, eternally spawning new universes. In this picture, while our time might have a beginning, there could be a broader concept of time encompassing the entire multiverse. At the other end of time, the fate of the universe also raises intriguing questions. Will the universe expand forever, leading to a heat death where all energy is evenly distributed and nothing interesting can happen? Will it collapse back in on itself in a big crunch? Or will something else entirely occur? Some speculative models even suggest that time could end. For instance, in the Big Rip scenario, the acceleration of the universe's expansion becomes so extreme that it tears apart all structures, down to the fabric of space-time itself. These cosmological considerations remind us that our everyday conception of time as an endless flow might not apply to the universe as a whole. The beginning and end of time might be more than just philosophical questions. They could be real physical events. 19. Time and determinism. The nature of time is closely tied to questions of causality and determinism. If the past completely determines the future, what does this mean for our concept of time? In classical physics, the universe was seen as completely deterministic. If you knew the position and momentum of every particle in the universe, you could, in principle, calculate the entire future and past. Quantum mechanics threw a wrench in this view with its inherent probabilistic nature. The uncertainty principle states that we can never know both the position and momentum of a particle with perfect accuracy. This seemed to introduce an element of fundamental randomness into the universe. However, some interpretations of quantum mechanics, like the many worlds interpretation, maintain determinism by suggesting that all possible outcomes of a quantum event occur, each in a different branch of reality. The question of whether the universe is fundamentally deterministic or not has profound implications for our understanding of time. In a fully deterministic universe, one could argue that the future is already there in some sense, just like the past. This aligns with the block universe view we discussed earlier. On the other hand, if there's genuine randomness or free will in the universe, it suggests a more open future, with time truly flowing from past to future as new realities come into being. This debate touches on deep philosophical questions about the nature of reality, free will, and the flow of time. While science can inform this debate, the answers may ultimately involve philosophical or even personal choices about how we view the world. 20. Living in time. As we conclude our exploration of time, it's worth reflecting on what all this means for our lived experience. How should we think about and relate to time in our daily lives? First, it's important to recognize that regardless of the ultimate nature of time, our subjective experience of it is real and significant. The way we perceive and interact with time shapes our lives in profound ways. Understanding the malleability of our time perception can be empowering. We can use techniques like mindfulness to alter our experience of time, potentially making it feel like it's passing more slowly and allowing us to savor each moment more fully. The finiteness of our time, the fact that we all have a limited lifespan, can serve as a powerful motivator. Recognizing that our time is limited can encourage us to prioritize what's truly important and make the most of the time we have. At the same time, some of the perspectives we've explored, like the block universe theory, might provide comfort in the face of loss. If all moments of time exist together in some sense, then perhaps nothing is ever truly lost. The cyclic models of the universe remind us of the importance of cycles in our own lives. The daily cycle of waking and sleeping, the yearly cycle of seasons, the life cycle from birth to death. Embracing these cycles can help us find rhythm and meaning in our lives. Finally, the deep mysteries surrounding the nature of time can inspire a sense of wonder and curiosity about the universe we inhabit. The fact that something as fundamental as time can be so puzzling reminds us of how much there is still to learn and discover. As we bring our journey through time to a close, I hope you've gained a new appreciation for the complexity and mystery of this fundamental aspect of our reality. From our everyday experience to the cutting edge of theoretical physics, time continues to surprise and puzzle us. Whether time is truly linear, cyclical, or something else entirely, one thing is certain: the time we have is precious. So let's make the most of it, staying curious, exploring the mysteries of the universe, and savoring each moment as it passes. This is Dev signing off. Until next time, whenever and whatever that may be.